So good afternoon, ladies and gentlemen. I'm very honored to be asked to address you in this keynote today. I want to talk today about a new trend in economy supported by very complex software and I can tell you it was not IT, this was just old technology screws missing. So a new trend in economy supported by very complex software IT systems, which are interconnecting the physical world and digital world. They create completely new business models that produce jobs and revenues. And this is the opportunity for the future. I will call these new software IT systems smart ecosystems. But they are related, and I will tell you how, with terms you know, cyber-physical systems, IoT, iOS, big data. And one thing I will try in my presentation is to get a little bit sense, a little bit structure into all these buzzwords. That's number one objective. And the number two objective of my presentation is to list some of the challenges these new systems pose for software engineering and systems engineering. I will structure my presentation in three major parts. First, I will tell you a little bit about the background I'm coming from, Fraunhofer Gesellschaft. Then I will talk about the path from Digital Society 1 to 2, the current path. And I will focus at the end on the challenges for software and systems engineering. So let me start with Fraunhofer Gesellschaft. Fraunhofer Gesellschaft is named after a famous German scientist, Josef von Fraunhofer. He actually was what you expect a Fraunhofer person to be, a researcher, inventor, and entrepreneur. He became famous for discovering the Fraunhofer spectral lines in the solar spectrum. He developed new methods for lens processing, and then he started a company to produce these kinds of telescopes which you see on the right side. By the way, if you have a chance to visit the eastern German city of Dresden, you will find an exhibition on these devices of Josef von Fraunhofer in the so-called Zwinger Museum. Just a few facts about Fraunhofer itself. It's Europe's largest applied research and technology transfer organization. It has about 70 institutes and about 23,000 employees, mostly researchers and engineers. And as you can see from the map, the institutes are distributed all over Germany. The most important aspect, however, is the form of funding. To do successful applied research and technology transfer, we have to acquire 70%, about 2/3 of our budget, by means of contract research. Partly European projects, partly projects directly with industry. And this, by the way, was designed in 1949 when Fraunhofer Gesellschaft was founded as a recipe for excellent applied research. And Fraunhofer was started after the Second World War to help German industry to get back on its feet. And ever since, Fraunhofer is considered to be the driver, the engine for innovation in all areas of technology in Germany. This slide shows you that Fraunhofer is not only present in Germany, but a few years ago we transformed into a European research organization, so we have presence in most countries in Europe, but also beyond. The focus outside Europe is currently on the United States, where we have 8 centers, and South America, where we have started in Brazil and Chile, the first centers. But as you can see, other parts like Asia, we have offices, but not yet big centers. The main focus areas are probably the same as in most other countries. They are interdisciplinary fields in the area of health and environment, mobility and transportation, communication and information, production, one of the strongholds in both Germany as well as in Japan, energy and resources, and safety and security. And Fraunhofer has a unique position to address these interdisciplinary areas because we have institutes in all areas of technology. Now let me focus a little bit on my institute, but you should understand by now, this institute, IESE, is one of the 70 institutes. Our focus is on software and systems engineering. This is one of the trends that has been coming with this IoT development, that you can't do software engineering in isolation, but it has to be part of system engineering. We have more than 200 employees, also mostly researchers and engineers, and we are located in Kaiserslautern, which is 100 kilometers southwest of Frankfurt, close to the French border. Now, what do we do for companies we have contract research cooperations with? We help them to create software-enabled innovations. This could be product, service, or process related. And the two cornerstones upon which we develop these innovations is engineering, to apply solid engineering principles also to the development of software. That's what software engineering is all about. And the focus on quality, and in this particular case, measurable quality. So measurement is an important aspect. So engineering plus quality is the enabler for innovations in many parts of our industry today. If you would ask the CEO of Siemens or Daimler, big companies in Germany, how much of their new products or services are depending on software, they would probably give you the answer 100%. There is no intelligent product, there is no intelligent service anymore, which is not significantly driven or enabled by software. Now, in response to these challenges, what are our competencies? Our competencies are in scalable system engineering. Scalable is important because it means we can apply it to larger and larger environments. When you talk about these IoT-based systems or smart ecosystems, we talk about huge, not just large, huge systems. So we have to have architecture concepts, we have to have testing concepts for extremely large systems. And we want to have these with guaranteed quality. And that's where our aspect of experimental software engineering comes in. We are testing and evaluating new innovative software engineering methods in the lab. So we do what every engineer would do. Before you release something into practice, you test it. You try to find out what are the strengths and weaknesses, what are the limitations, before you give it to companies. And I believe this is the basis of the success of our institute, because by testing it in the lab, we reduce the risk for introducing new methods or approaches into practice significantly. And we apply this to all companies that are based on software, where innovations are based on software. So in a little bit more detail, give you a few details in terms of scalable system engineering approaches. We focus on the early activities. So requirements engineering, so architecture as the cornerstone of maintaining complexity, and processes, which means model-based development, so integrating the different phases of development. On the side of quality, we focus, as you might imagine, on safety for embedded systems and on security and user experience for the information system part of these systems. And here you can see smart ecosystems we interpret as the integration of the physical world, embedded systems or cyber-physical systems, and on the information system side, including mobile applications. These two worlds are growing together. Now, just one aspect on evidence. How do we produce evidence? We view ourselves not just to produce new methods or approaches, we also want to create evidence. And what you can read down here, we analyze real software and systems in collaborations with our industrial customers, and we do experiments in labs. And all this is aimed at creating quantitative evidence so we can support our companies in making decisions. So if they need to make a decision about innovation, we can say which of these new innovations is better fitting or worse fitting. I know you probably realize this is new maybe in software engineering, but it's not new in engineering. We are trying to apply very systematically engineering principles, including creating evidence before you go into the real world, into practice, also to our field. So, this part was to give you an overview from which environment we are coming and what the specific focus is of our specific institute, IESE. We are collaborating now for 10 years together with IPA here in Japan, and we are also working in Germany with companies like Fujitsu, Hitachi. So now let's talk about the trends we are observing. We are actually in the middle of realizing this trend. So when we talk about digital society 1.0, what we have today, we observe this both in our personal but also in our work life. So in the personal life, we already experience today that each one of us is working with several electronic devices. We use these different electronic systems, however, they are badly integrated. So for instance, I'm traveling a lot. All my appointments are in here, but I still have to go to my car and input the destination where I have to drive at 10 o'clock. Why are these two systems not integrated? Why is my navigation system in the car not knowing that based on my calendar entry I want to go there? Very simple thing, yeah? And you will find many of these things, we have lots of devices, but they are not integrated, they are not supporting entire workflows. Now, when you look at the same thing in the business world, we can see already lots of developments. For instance, workflow systems, whether it's SAP or whether it's from Oracle, are integrating different parts of a company, of the supply chain, from suppliers to OEMs. We also see in an area in which we are very active in smart farming, where we have lots of integration between, let's say, a tractor and the implement, the device in the back. Actually, we have even reversed almost the principle in context of precise farming, precision farming. The implement is driving the tractor because the sensors at the implement detect whether you are too far left or right and then tell the tractor to countersteer. Yeah? You can imagine this only works automatically if the two, tractor and implement, follow a standardized protocol for informing each other. So what's happening if a John Deere tractor has a Fendt implement? Can they work with each other? So taking the next step from just integration to real integration, we developed a cloud application where if you plug an implement from Fendt to a John Deere tractor, they can check the protocols, they can follow. And if they have a consistent protocol, they are allowed to drive automatically. If not, they have to drive manually. So we see steps in that direction everywhere in the business world today. Let's step back. The trend is physical objects get what I call here digital life. Physical objects are things, living objects, people, etc. They produce data, have a history, so with the history I can predict things more precisely. And they can also take actions based on data, context dependent, location aware. I mean, I gave you the example of the truck. That was context dependent when I put together to implement and a tractor from different companies. It's location aware, I know where they are. I have to be able to do this in real time, and I have to do this across boundaries. Just to give you a sense of how big that space already is, I show you here a chart from a German company, Bosch Software Innovations. That's a special subsidiary of Bosch from 2012, where they try to point out 3 types of networks. Internet of people, so what you see here, social webs are part of such internets. Internet of services, Internet of things, we see smart home, smart factory, or smart grid. Grid in the context of energy management. And the numbers here show you the volume of elements or objects already integrated today. So millions. And so if you anticipate the future of this, we have systems that are of tremendous complexity, both on number of people involved, number of physical objects involved, and number of data involved. Now, I would like to come to probably one of the most important charts to explain a little bit the terminology. Now, this was the view when I started in software engineering. We had 2 completely separate worlds. We had information systems and we had embedded systems. Embedded systems were driven by safety requirements. The information system world was driven by security, data security, availability requirements. But they were not related at all. So, including mobile systems, we started the integration. And cyber-physical systems are basically systems of embedded systems with an interface to the information system world by being able to access the internet. So it's a small approach to the boundary of this other world. The same way, we developed so-called emergent systems, that's systems of information systems. And they also approach this interface to the physical world by using RFIDs. The most prominent system of these emergent systems software is logistics systems that were using RFIDs so they could track packages wherever they were. Yeah? So they had an interface to the physical world, but they were not really interacting with the physical world. So depending whether you come from engineering, then this was the term of choice. When you came from information systems or IT, this was the word of choice. But this is, I would call, evolutionary. Because due to that integration, you can do things a little bit more efficient. I can find out whether a package is not on its track to its target destination. But I can't yet create new business models. That's why we are here today, building parts of these cyber-physical systems and emergent systems. But the real benefit will come if we fully integrate them. Yeah? Now let me give you an example what the difference is in the trucking business. We work with Daimler, which has its largest truck factory in our state. In terms of maintenance, today we have enough sensors on trucks, like in every car, that you can watch how certain parts of the truck are doing, whether they get overheated, whether they lose traction, whatever. And you could use this data to predict that maybe a certain part will fail within the next 1 or 4 weeks. But you have to interpret this yourselves. if you decide that part will fail, then you can call the logistics system and say, start the process of getting that part which we have to replace. And then eventually you replace it. But they are isolated. In a smart ecosystem, you would have access to the historical failure data for the last 5 to 10 years, which would allow you to make a much better prediction whether and when something will fail. In addition, you would automatically trigger the logistics system to start the retrieval of this part, maybe even production of this part, depending what it is. And when the part has arrived or will arrive, I can find out at which position this truck will stop, have its next stop. Yeah, because they have to sleep once in a while. And then you send someone to repair that part while the driver is sleeping, so you do not lose a single hour of operation. Yeah? And you can actually create a new business model. You can create a company whose sole purpose it is to offer a service to trucking companies that they do their maintenance without loss of operating time. Yeah? They only have to have access to the data from the car, they have to have access to the data from this logistics supply chain, etc., and can offer the service. And this here is therefore the real revolutionary part. With what I call CPS, or merchant systems, we will only be able to do things more efficiently. That's nice in itself. But the jobs of the future lie in this area, where you create new business models, new types of companies. Yeah? And so the challenge to us, and here I say always, Japan, Germany as traditional engineering companies, countries, are in the same boat. Because if we leave it to the Googles to make this last step, then our engineering companies will lose. Some of you know probably the Google car, where Google is currently experiencing how to work on mobility. They have really understood that the essence is in that software and the data. If they have developed their business model, then they buy Daimler or buy Toyota. They have cars immediately if they need that. Yeah? So people think they are funny because with a toy car, they only use toy cars because they know in the car that's not the important part. The important part is the business model, interconnecting all these ecosystems. Yeah? And so if we leave it to the IT companies, they will be much faster. They have different innovation cycles than engineering companies. I will talk about Industry 4.0 a little bit later, which is invented in Germany, the term. But currently we have a disillusion because it's realized that it's much too slow. And now there is more activities to put together the top engineering companies and the top IT companies to speed up that process of coming up with business models to actually develop or be in the lead for these kinds of applications. And finally, big data is of course very important to develop these new business models. As I say, cyber-physical systems or smart ecosystems are the engines of the economy of the future. Big data is the fuel. Yeah? The capital is going to be data, and companies like Google or others have identified this much earlier than most engineering companies, but very often the majority of data comes from cars or other things, from the engineering companies. So they have to decide very quickly how they want to handle the ownership of this data. Do they just give it away to someone else, or are they using it for their own business models? Leading automotive companies like Daimler, I'm sure Toyota too, but I know the Daimler case, are already working on mobility models for the future that include that. Yeah? And just adding the term of IoT and iOS, I mean, this is not a smart ecosystem. This is the platform upon which you can work, IoT or iOS. Yeah? So I'm putting up this chart because very often I'm confronted with a mixture of terms. IoT, big data, cyber-physical systems, everything is put in the same box. Understandably, because from different perspectives, that's the aspect you might be interested in. But what I've tried here is to kind of put things together to provide kind of a reference what we are talking about, and also what is the important step, that is this step. Yeah. When you stop here, you only have done an evolutionary improvement of efficiency, but you have not created the new business models that will drive the economies of the future. So when we put this into perspective, that's what we call Digital Society 1.0, 2.0. We are currently experimenting in reality. I don't mean us as researchers, but the real world, in building up these cyber-physical systems in certain examples. Or information systems. Some already are a step ahead when you think of this Uber case, this system where you can basically order your taxis, but you can also become your own taxi driver and offer your services. That's already steps in the next direction. And this is, again, where this revolutionary part will happen, where all these new companies, these new business models will develop. By the way, if you want to read a book, and I'm advertising now a book not of myself but someone else. If you know Jeremy Rifkin, he is an American macroeconomist. He wrote a book, The Zero Marginal Cost Society, where he describes some visions where the world by means of this integration could be in 5, 10, 15 years. Then you will recognize that we are currently only scratching the surface. And I claim that as high-price countries, high-salary countries like Japan and Germany, we have to be in the driver's seat. We can't follow. Otherwise, we lose our edge, which has tremendous consequences for the entire societies. Now, Industry 4.0, again, is just one possible smart ecosystem. I like to talk about smart X because every area will become smart in this sense. And so in the production area, we talk about Industry 4.0, smart farming, other examples, smart mobility, smart health, smart energy. For example, currently we are developing a large European project to develop the reference architecture for the future European energy system. This is based on the assumption that moving towards renewable energies, this will be a highly complex, decentralized system to manage. And this is very similar to the telecommunications architecture. You developed standards, interface standards, so different providers can plug into that system and the overall system functions. Today in smart energy we have proprietary solutions from industry, but they are not standardized at any level, so if you would plug them together, the system wouldn't work at all. So, just using two examples very briefly in the area of smart cars. What's the main distinction between the situation 2011 or 2020 anticipated? Today, it's what we call a closed ecosystem. The customer, the owner or buyer of a car or leaser of a car pays for everything, insurance, etc. In the system of tomorrow, because you can exchange all these data, we will have a so-called open ecosystem, and new players can actually participate. So for instance, you could imagine a company that offers you the best rates for insurance based on knowledge from the car, how you are driving, and based on acquiring the best insurance policies. You would have an insurance which dynamically adapts to where you are driving, how you are driving, etc. So in some sense here, the owner of the car doesn't pay for everything. Partly it's paid by making data available to others to perform their business model. So this company providing this dynamic insurance is basically doing this based on data they will get from the car, from the user, etc. The other example is based on lots of work we are doing with John Deere. John Deere has its European Research Center in Kaiserslautern, so we are working towards autonomous driving, but also service integration. And so let me just mention two things. The first one on the left side is this preventive defect avoidance. This is the system I discussed with you about trucks. But this is even at least as important for machines in the farming environment, because let's say a harvesting machine is only used 3 months a year. And if you would have to bring them to a garage for 3 days to get repaired, that would be a tremendous loss to the owner of that machine. So they are very interested in doing this diagnostics, being able to get the parts in time and replacing it without loss of operating hours. So this is one model we are developing with them. And the other thing is, how can we optimize harvesting logistics? So for instance, considering influence of weather, influences of which machine is at which location. Even today, when fertilizing is done on the farm, they are using historical databases about the fertilization in the last 10 years, so they can bring out exactly enough, not too much fertilizer, to make sure that the soil stays healthy. So, Industry 4.0, it was actually publicized in 2011. This is a picture from the Hanover Fair in 2013, where a kind of white book or plan was handed to our chancellor. And this research initiative is trying to find answers to 4 major challenges: the global competition, the resources shortage, so you have to collaborate, the demographic changes, especially in Germany and Japan, we are the leaders in on that side, and urbanization. And the idea is to identify and plan and prepare software and IT for roles in production facilities. So this is the smart ecosystem for production. You probably remember the basic reason why we call this Industry 4.0. I mean, the previous 3 revolutions were at the end of the 18th century, when the steam engine was invented. That is considered the first industrial revolution. Then at the start of the 20th century, the industrial revolution, or the second one, based on electrically powered mass production. And the third one is not too long ago, in the starting in the 1970s, where IT was used to increase the level of automation. But if you ask me what's the difference between number 3 and 4, number 3 was, if you remember my chart, more on this level of interconnected physical objects. So machines could talk to machines. But there was not much intelligence. So what the Industry Revolution 4.0 is bringing, due to the interconnection, that you can include all kinds of information from all kinds of databases through the internet. You can include collaboration with your customers, with your suppliers. So the entire value chain is covered. And that, of course, provides much more intelligent automation than was possible in what was called Industrial Revolution 3.0. The main characteristics are, I come back to this, so-called vertical and horizontal integration. I will talk about this on the next slides. And the focus in Industry 4.0 is that this has to be real-time capable. You have to be able to make decisions in real time, comprehensive, covering the entire supply and so chains, intelligent, use information, historic information, context information as much as possible, this horizontal vertical integration, and network all objects, from people over machines, objects, and IT systems. So Industry 4.0 is not, 4.0 is not about machines communicating with machines, but there you also have machines communicating with parts. So you have a chance to optimize the production, minimize resources, etc. And do this for dynamic management of complex systems. coming back to these levels of integration, the vertical integration actually refers to the fact that you try to integrate different levels in your enterprise through all levels of control. So what you see here is from finance over IT all the way to production and distribution. So there has to be a clear integration, automatic integration across all these levels. And based on a study by Pricewaterhousecoopers, the possible gain measured in terms of how much more is automated, is digitized. From 2014 to 2019, they predict an increase from 20 to 80% in factories, in production environments, in companies. But there's also horizontal integration along the supply enterprise customer chain, so end-to-end integration in that sense. This is also a chart from the corresponding chart from Pricewaterhousecoopers, and here you see they predict a similar increase in digitization or in automation from 24 to 86%. So high potential from that point of view. So what is it? The vision of industry in 2025 is, that's the horizon of this white book you just saw, handed by Mr. Kagermann to our Chancellor. One of the prime things is flexible individual manufacturing. So the idea is to increase customization, which is the demand by customers, at reasonable cost. The second thing is to have connected enterprises and support them. We see a trend more and more that you will not only have static relationships, you have one supplier, one OEM, but that you create relationships dynamically to exploit a certain opportunity in the market. So the example, for instance, the Olympics 2020 in Tokyo. You could imagine that a travel agent, airline, hotel, and so just create a virtual organization for 1 or 2 years to exploit that market. That means you have to be able to integrate this to be interoperable to a very high degree. The third one is competitive advantage of flexible value creation networks. And by the way, here's a chance also for smaller mid-sized companies, because a small supply company in the automotive world could be part of multiple smart ecosystems. The one for Daimler, the one for Toyota, the one for Chrysler, whatever may be. We also have to make sure, or can expect, that we have a coexistence of open and closed production networks. There are certain things where you are open, exchange data. There's other things where you collaborate, but you want to protect your IP. Also, and this is related to our demographic changes, having more and more elderly people, the assistance systems that are being developed as part of this make certain jobs easier. So, work comfort through intelligent assistance systems. And this is, from an economic point of view, the most important one, that it offers these new opportunities for companies. I mean, something like Uber, something like this company that provides zero loss operation maintenance, which I sketched for you in the trucking environment, would have been unthinkable 5 or 10 years ago, because we didn't have the means for interconnection, the means for collecting these data, which all came with miniaturization of sensors. So here, again, a chart from Pricewaterhousecoopers, and basically they were asking companies about the expected benefits. And what you can see here is that the top mentionings with 80% high impact is better planning and control, high customer satisfaction, and large flexibility in products, which is partly related to this customization. So there is an expectation that there is a huge benefit. What's the return on investment really? And this is a questionnaire or inquiry made by Bitkom, which is the German IT society. And they were asking companies, what do we expect in terms of growth? Yeah, more revenues, growth. And what you can see here is that at least in Germany, these four sectors, from chemical industry, automotive, machine plant construction, electrical equipment, that's not a surprise. These are the standard sectors of industry in Germany. They expect an increase from 2013 to 2025 of 20. In automotive, it's 20, 30 in the other cases increase. So what you can see is an annual growth, when you break this down over the years, of between 1.5 and 2.2% growth, just based on that digitization. This is typically beyond the normal growth countries have in those economies. Now, opportunities and challenges. Opportunities are there. What are the challenges to meet them? And I've just highlighted 6 here because they are very much related to what I'm talking about otherwise. Standardization. If you want to create these ad hoc company networks, of course you need standardized interoperability. Otherwise, this is impossible. You need work and process organization. This means both physically but also IT-wise, the support, control of these. You need new business models. Yeah? We are thinking very often too much in continuing doing what we are doing a little bit better. Yeah? Here we have completely new business model opportunities. Security and know-how protection. I believe this might actually be one of the most deciding criteria, at least in Germany, but I think that's the same everywhere. That you want to benefit from the data of others, but you don't want to show your data to others. Now, here we can look back a little bit on our 10-year experience with IPA, where we talked about measurement of processes, etc., in the context of process improvement. And we have learned that just putting data into a container doesn't help. You have to be able to define the objectives, what you want to do with this data. You have to decide who can access which data for what purpose. And I think this will be the solution also for big data. Big data will not be to put everything, huge amounts of data, in a big pot and have intelligent algorithms find something. But you will have to organize big data, especially if you want to make real-time decisions. And here we actually have solutions that came out of our previous work, and we have just developed the so-called data usage control approach, which got the highest European EATO Innovation Award, which, in addition to encryption, to access control, which is much too static, allows to define policies. So if I, for instance, drive a car which has sensors to recognize whether I'm physically in bad shape. So if I have a heart attack, the car could be driven into a safe state on the right side of the road. However, I want this data to be used for that purpose, but I don't want that data sent to my employer. So I don't want my employer to know what my physical status is. Yeah? So I have to be able to describe, as the owner of that data, whether it's the car company or whether it's me personally, what can be done with this data and what not, and under what circumstances. That's a much more flexible model for data control than to say, you can access everything, I can't. That's much too static to exploit those business models. I personally, if I would have to bet my money on one thing that could be the success factor or the hinderer of this development, I believe it is coming up with smart solutions for data usage. In addition, and this is again where Japan and Germany are in one boat, we have a high lack of top-level experienced personnel. And this will certainly even increase given the demographic changes in both of our countries. So we have devised here in Germany, for instance, both changes at universities, that we have more system engineering, and I'm glad to hear that here is someone from system engineering program. We are still too much centered in computer science, electrical engineering, mechanical. Yeah? If we really understand that the future systems are in that integrated world, we also have to prepare students for that new kind of world. And in addition, I believe in both countries, we have a huge number of very good, very experienced engineers who more and more have to do software. And they are not really prepared for that. So we are now building up continuing education programs where good engineers in companies can actually in distance work, I mean, besides their normal work, get a degree on what we call software engineering for engineers. So we can reuse kind of experienced engineers also in this new environment, because we can't just wait for more output from universities. That takes too long. Yeah? And research, I don't know, I mentioned just the data access or data usage control problem. There is so many aspects, and I will come back to this in my third part, about new challenges in software engineering and systems engineering, that we are far from being able to solve all these problems today. In my world, in software engineering, over the past 10 years, the world in terms of what are the key challenges has changed so much that if we would still do the same things we did 10 years ago, we would not be of value to companies today. So let me focus on my personal area, challenging for software and systems engineering. Let me just start with this slide just as a reminder. We will increase the percentage of digitalization, data, algorithms, software. Software is at the core by 50% in only 5 years. So what's the challenge? This is my summary of challenges, and actually I will add a sixth one. I will explain in a second. So let's start on top, complexity. When you think of complexity, it's not getting a little bit bigger. It's getting exponentially bigger. And there are even parts in these systems which we don't even own when you talk about open systems. So the topics of architecture, and in this case system architecture, becomes crucial. In addition, model-based development. This was a topic for a long time, wasn't taken too serious, but now people understand this complexity of system we cannot handle unless we work with abstract models of software. And just to make it clear, when I talk about system engineering, I do not mean hardware engineering. I mean the abstraction from hardware and software. I have experienced this many times when I go to a company, automotive company or similar company, and then my question is, show me of your product, problem with the system architecture. What they then show me is the hardware architecture. I say, no, I mean the system architecture. Then they show me the software architecture. No, so they don't have a system architecture. This might have been okay, while software was a small, minute part of the system, because then the hardware architecture is close enough to system architecture. But lots of the problems we have today in recalls is a matter of fact the result of putting more and more software on the system, on the hardware architecture. And because there are buses through which that software is communicating, you establish all kinds of unspecified relationships. So if an OEM like Daimler gets devices from 10 suppliers, and they all have implicit interfaces, it's sheer luck if you find all the problems in integration. Yeah? So for these complex systems, we need to have an abstraction layer where we talk about the architecture from a system point of view, above hardware and software. This is the place where you can do most of the optimization, not within the hardware, not just within the software. Next thing is uncertainty. Where does this come from? We will more and more see systems that change during runtime. I myself was involved in building software for satellites, etc. They were complex, but you could test everything, quality assure everything during design time, and then it was shipped to the satellite. Today we have systems that will reconfigure during runtime. So, if reconfiguring is not the problem, but reconfiguring and still being sure that you maintain quality of service guarantees like safety, how do you do this during runtime? We need runtime capable ways of evaluating or assuring or certifying certain levels of quality. Otherwise, we will not be able to do it in the context of these new systems. Another thing is the merger of these two worlds also forces us to model safety and security in an integrated way. If you have today to certify a car for safety, but behind that is an interconnected system of systems with connections, yeah, then security problems can cause safety problems. Now you would say, then we model security. The problem is safety we can model very well quantitatively. We can do this for very large systems in quantitative terms today. Security is much harder to model quantitatively because it very much depends on the perception of guys who want to do wrong things. Yeah? But we have to do it, otherwise we will not get these systems certified. Diversity. These large systems consist of software from very different stakeholders. Different people are developing it, different languages, different methods, whatever. And you also have parts of the system which you don't even own, which you don't even know, and you still have to make guarantees for the overall system. And last, so interoperability, by the way, is for these kinds of heterogeneous systems configurations essential. And by interoperability, I mean syntactic and semantic interoperability. Smart data usage, I mentioned this already. I didn't call it big data usage on purpose, but smart data usage. Because big data is determined by three different dimensions, not just the volume of data, but the heterogeneity of data, having very different data, and also the speed in which they arrive. Are they more offline? Do they come in real time, etc.? So big has very different meanings in that context, not just volume. And using them smartly, I believe you need filters. You can't just look into the entire box of data. And I mentioned before our GQM approach, which we used to target to focus measurement for process improvement, could be an enabler to also provide a filter to look at data in the context of big data. The other one is the level of aggregation. You know, I might be willing to exchange aggregated data with my competitors, but I'm probably not willing to exchange the raw data. Yeah? By aggregating, you can basically anonymize your own data. So I think describing the purpose of analysis for big data and describing the appropriate level of exchange is the two components to a filter that will make big data into smart data. And I added this, user experience, which is a topic in our institute. And the reason is very simple. In these smart ecosystems, you do not have just very specialized, trained people using them, but a very wide, heterogeneous range of people. So you have to be able to develop systems that are fun to use, that people without too much training can use. I give you a citation. The company John Deere, which I mentioned frequently, one of the biggest buzzwords in research and development for them is user experience. You will be surprised because you expect this from Google or Microsoft or SAP. But because they do not only provide machines but provide services managing a farm, they get into the same situation that they have to worry about. Is the customer interested? Is it easy to use our systems? Yeah? This again, from this merger of the physical and information system world, also leads to adopting concepts that were before only in the information systems world. Now they affect everybody, even companies like John Deere, a very traditional, very typical product engineering company. So, just a few things to outline also the topics we are addressing in our institute. So the first one, I'm referring here to these five, is complexity. So smart ecosystems are the most complex artifacts created by human beings so far. I mean, there is nothing that exceeds this in complexity. Dynamics and long lifetime require a high degree of complexity reduction, and that's something you can do either by means of architecture or by means of abstract model-based development. So, to nobody's surprise, we engage in model-based engineering approaches, for both components, the embedded as well as the information system side, scalable architectures. Scalable, it was important all the time, but now everybody understands that without it, you cannot survive, and mature development processes. Diversity, this was the idea or the challenge that smart ecosystems comprise and integrate diverse systems and stakeholders across companies and domains. I mean, you could have a supply chain, supplier, OEM, and customers. You could also have an integration of companies in the same domain. I know, for instance, of smart ecosystems in the PR and marketing aspect, where companies in the same domain put their marketing data into the same cloud, and by combining them, they get better predictions of the market. But only the aggregated information about trends in the market are exchanged, not the raw data. So this requires interoperable architectures. You have to be able to plug together individual components without loss of quality of service. This is, by the way, this energy management system for Europe. We have to be able that new clusters get plugged in without sacrificing availability or safety security of the system. We need standardization, otherwise the effort is just too high to integrate different companies. And we have to combine this with quality of service guarantees. Yeah? I mean, all these new aspects are easy in systems where you don't have quality of service requirements, dynamic adaptation, etc. But if you have to combine that with quality of service guarantees, like in the embedded product world, then this game becomes interesting. So, last uncertainty, next uncertainty was the third one. So you have to be able to deal with uncertain environments, players, and how to interact with them. And this is also related to the fact that the system can reconfigure as a result of new concept. So here you need flexible architectures. You probably remember the term product line engineering, but that was used during design time to anticipate different versions of a system. It's not happening during runtime. Now we have different configurations during runtime. By the way, in the automotive industry, I know this from German companies, we already do this. So if a sensor is failing in a car, we reconfigure the system, but we only reconfigure it across a small number of during design time quality assured versions. Yeah. And that's much too limiting for these new systems. Here we will have configurations we haven't thought about before. So we have to be able to, for instance, assess the quality certificates or certify the qualities during runtime. Adaptable systems, that means they do not just have to be interoperable, they also have to be able to adapt to new environment changes. And this is one way of probably connecting development or design time and runtime. We have to have the ability during development time to simulate systems or system configurations, situations in context, to actually anticipate what kinds of things we have to be able to react to. Safety and security. This is one thing that is has still some, I would say, big challenges. And I would say the biggest challenge is what I said before, that one of these things is easily quantifiable, the other one not. We need and are developing integrated security safety models, where we model risk cases with respect to security. we also need and develop more flexible, context-dependent data usage control approaches. This is the approach I was referring to, where you can define the policies, what must or must not happen with your data. And we have developed an approach for critical systems to isolate them, so-called software cages. So you remember, this idea is lent from the area of robotics. If you have a robot in a production environment and you're not sure it works all the time, you build a cage around it so nobody gets killed. And the idea we are developing, or the solution we are developing with some customers, is to build software cages. So if you have an area, subsystem in your system that might change over time, reconfigure, you could build a filter with very elementary building blocks around it that checks whether there are triggers, data sent out, that are not sensible. So basically you assure yourselves against wrongdoing of this new subsystem, newly configured subsystem, and protect the rest of your system. But this is something we are currently experimenting with. This is not yet production ready. Finally, big data or smart data, smart usage of big data. I described here, which is common sense, that the term big means three things. You see the volume dimension, you see the variety dimension, so having heterogeneous sets of data, and also the velocity, where you can basically say I can access data in batch mode, and the most extreme is obviously in real time. And to deal with that, we need to have business models. We have to have strategies. I mentioned before, we have to have filters in terms of what are the objectives of big data analytics, and we may have rules for abstraction. We need approaches for managing data. I mean, just managing data quality, I should say. Not just garbage in, garbage out. So if I allow all kinds of data be put into my box, I cannot expect to get good results. And integrated data usage control, this is again the idea of this more flexible security concept focusing on data control. Let me just sketch something that has accompanied me throughout my life. You probably know the famous Gartner curve. For any innovation, we observe a certain trend. The trend is initially there is a hype. Everybody believes that will solve all the problems. Then there is disappointment when we realize it doesn't. And then we figure out how to do it well. My interpretation is that with respect to big data, we are somewhere here. Currently there is an incredible hype that everybody believes if they have lots of data, they will solve all their problems. Now I'm sure we will have a big disappointment eventually. Think of car manufacturers. They produce so many data. If they deliver them freely to the world, to Google, for instance, there will be a situation where someone will sue the company because wrongdoings happen based on this data. And I believe that we have two kinds of things to influence, not to solve, but to influence this turnaround. And this is actually what I mentioned before, this GQM approach, to focus the evaluation of big data. And the second one is this data usage control mechanism, where you can define in a very context-sensitive way how data should be, should not be used. Okay. Those who know me well know that from my RICO time, I'm a small fan. So I just used this picture to describe the challenge that says, yes, there are lots of opportunities, but you also need to have the capabilities to exploit them. Yeah? And this is a funny picture, of course, but it describes that discrepancy. Today, everybody talks about the challenges, the opportunities, but there is not much realization what it needs to be able to develop the capabilities to actually take advantage of this. Yeah? And I mean, if I go back in my slides, I would put this as the core slide. Companies have to realize that the key to being leading in that smart ecosystem world is software. Google has understood this. That's why they are practicing this mobility concept with toy cars. Because the advantage is not in improving the cars, it's improving what happens between cars, their users, their developers, their producers, etc. Yeah? And if you want to be leading in this field, and software plays a major role, is the main driver and enabler, then you also have to be the best in software system engineering in your domain. Yeah? The same way as in the last 50 years, Germany and Japan have prospered in the car manufacturing business. And what was the key? I mean, you can manufacture cars cheaper in other countries. But why are we still producing cars? Because we have the best process technology, construction, production technology. So people trust in the quality that comes out of our production processes. Now, if future products have an increasing part of software, it's no longer sufficient to be the best in producing hardware. You also have to be the best in producing software. Yeah? And I think this is the challenge for everybody who wants to be a player in this new ecosystem world, that you have to be in the driver's seat also for software. I think that has to change the mentality in companies where software and software engineering so far is a subordinate role. This already starts when you see where software engineers are placed in companies. The offices of software engineers are very often in the basement, somewhere close to the basement. We have to be elevated to the same level, because the new business models are not decided based on hardware considerations, and then you do the software, but you have to exploit the opportunities from both perspectives. So you have to involve software experts, people who understand that from the very beginning. Yeah? And I will claim that an engineering company of the future that doesn't have a software expert on the top level will not be competitive. Yeah? That's to me an indication. If you are in a production company, you always have someone in manufacturing on the top level, because that's a core competence. We have to understand that software becomes more and more of a core competence. And that has to be reflected in organization, in processes, in everything. Okay, so let me go back. So before I summarize, I would like to mention one repeat and one aspect. The repeat is with respect to human resources. I truly believe that we can develop all the technology, all the methods. If we don't have enough people to support this, we will not win. So both countries, Japan and Germany, Japan need to think about how we can actually provide enough expertise. And I have given you hints in terms of university education as well as continuing education to reorient people. And the second thing that worries me probably even more is who decides on the speed of this development. And you can see, as I mentioned, that in the US the activities are faster because they are driven by IT companies who have a different life cycle thinking. In Germany, they were driven by very traditional engineering companies. And we just recently have decided that this is not going to lead to any success. So now we are putting together consortia from leading engineering companies and IT companies to push this process even further. And in our internal discussions, I already said that I believe that between Japan and Germany, besides all competition, there is enough joint interests that I could even imagine that we establish eventually a joint commission between our leading engineering companies and IT companies to be the leaders in this development. And there is two reasons for that. First of all, otherwise we will lose our stronghold, which is engineering. We have to be the leaders going to smart engineering, which is that buzzword Industry 4.0. But we also have to do it in other sectors of industry, because otherwise the job creation, the new jobs will be created somewhere else. We as high price, high salary countries have to be at the top level of innovation and not at subordinate levels. Yeah, we can outsource component development somewhere else. But if we are not in charge of the engineering level, of the top integration level, we will lose our future. And that's why I hate to just talk about Industry 4.0, because it looks like this affects only one sector. The term smart ecosystem also shows this is not for one sector, this is for all sectors, for our entire society. And we have to decide where we want to be in the lead in the next 5, 10, or 20 years, and then try to establish mechanisms, infrastructure, but also building platforms, also building application solutions in certain smart ecosystems. And again, in that boat, and that's where I want to close, is we are in the same boat. And I would actually like to also use this opportunity to thank IPA through all its representatives here, because I think we had a very fruitful collaboration in the past 10 years, focusing mostly on process improvement. I'm very happy that my I can say old friend Kadayama-san is here. We have collaborated even many years before that. And I think we have a joint interest to expand our collaboration into specific areas that are related to these smart ecosystems. Thank you very much.